Hey guys, hi everyone, welcome. It's the third day of the conference, and I'm really glad to welcome you here on the talk of this wonderful, fine fellow. Hi, Anthony.
Oh,
Thank you so much for being here. I'm not sure if you need the introduction, but just in case if some people, for some reasons, do not recognize you, I will do some. So I will say several words. Like Anthony is the world-known C++ expert. He was the multi-threading expert of the contributor to several Boost libraries and maintainer of several Boost libraries. He's the author of a really great C++ in action. What was
concurrency in action.
concurrency in action? Yeah, I was thinking about multi-threading, but I'm like, no, that's not true. Sorry, it was a while, and yeah, we're all looking forward to read the C++ 20 edition. And this talk, as far as I understand, is a small peek to this part that will explain and demonstrate how to use concurrency in C++ 20. I'm super excited to hear it. Thank you so much for being here. And so, how are you?
Well, I'm good. Thank you. Yes. I'm glad to be here. The first time I've been presenting at C++ Russia, so that's quite exciting.
Yeah, I can see again. I can see sun there.
Yes. Yeah, no, we've got a sunny day today, and it's been raining quite a lot recently, so it's quite nice to have a bit of sunshine.
Yeah, we can only envy you from St. Petersburg.
Yes. You get a lot of rain.
Yeah, well, rain, snow, all this fog. But
Yeah.
in St. Petersburg, it's much easier to survive because you can just drink all the time, so it's not really a problem. So yeah, when the offline conferences are back, we will try to show you, demonstrate why it's easier in St. Petersburg to survive this weather. Yeah, sorry for chatting so long. We just really want to hear your talk. So what do you say? Can we start? Are you ready?
Yeah, I'm ready.
Yeah. So, поехали. Off we go.
Okay. So, C++ 20 is the latest C++ standard. See, it's now 2021, so it's actually been officially a standard for over a year now, but it's only just coming to compilers and things like GCC and the latest version of Visual Studio support lots of C++ 20 features. So I'm going to be talking to you today both about the concurrency features that are in C++ 20 and then a sneak peek at things that we're going to add for future standards. And obviously, the things for future are not finalized yet. They might change, but we're going to have a look at the sorts of things that are under discussion. So let's start with the new features that we've actually got in C++ 20. And start by saying that C++ 20 as a whole is a huge release. There's a lot of new features, both concurrency related and not concurrency related. And we've got a lot of stuff there, lots of enhancements to the constant expression facilities from constexpr. We've got coroutines added to the language officially for the first time. And so there's a lot of extra features in there. But specifically from the point of view of concurrency, then we have several new library facilities. We've got support for cooperative cancellation, so that you can say, yeah, I know that you're running this task on a background thread and I want to cancel it. I want it to stop. And then the background thread can then check that it's been cancelled and deal with that in an appropriate manner. We've got a new thread class that automatically joins, and that's been one of the long-standing problems that people have expressed about the standard thread class, was that the destructor doesn't join it. If you don't explicitly join or detach with the standard thread, then the destructor of the class will actually terminate your program. And so we have the new thread class that avoids that problem by automatically joining. We have some additional synchronization facilities, new library features for synchronizing. We have updates to atomics, and then of course we have coroutines. And though the coroutines are not inherently a concurrency feature, then they certainly can be used for concurrency. And so they're on my list, things that are going to be useful for concurrency. So first up on that list was cooperative cancellation. And just by and large, then you often have tasks that you wish to cancel. You might have a GUI, it might have a cancel button. And for long-running applications, we might have a cancel button for short-running tasks as well. But particularly if you've got a long-running task, you're downloading a file, you're processing a video, whatever. You've got something that's happening, you want to stop, you hit the cancel button. And you want that task to actually stop. And so there's lots of ways you can do that. Obviously, people have been doing this in their software for years. Ever since there've been background tasks running, they've found ways to do it. But we're now adding a standardized facility to make that easier, so that then it's the same mechanism that you can use whatever your operations are. Obviously, you don't need a GUI to want to cancel operation. You might have background tasks that are you have a command line application or a server application that's got some processing that you want to cancel. It might be that you've started multiple ways of doing a calculation, and when one of them comes back, then you need to stop, or you've got an error signal saying, well, actually, that bit of hardware that I'm talking to has gone offline, and so therefore I want to cancel the preparation of data that's going to be sent to it, or whatever. And then lots of operating systems often have a way of forcibly stopping a thread. This is a sort of a really serious brute force mechanism for terminating a background task. But the problem with doing that is that then that's undesirable. It leaves your whole program state in an indeterminate state. You don't know whether that background thread had started writing a file, finished writing the file, whether it had started accessing a data structure, made some partial modifications, or whether it actually finished its modifications. Anything that was touched by that background thread that you've forcibly terminated is now in an indeterminate state. So if you can just completely throw away all the data that it was touching, and because I'm aborting this task, so I can just throw it all away, well, that's fine. But in lots of cases, then you can't do that brute force clearing the slate. And so you want to have a means of stopping the thread which is nice, friendly, tidy, that makes sure that everything is left in a coherent state at the end. So in C++ 20, we have a feature for this. We have standard stop source, which is a source of stop requests. And then we have a stop token, which is the other side, where you can say, have I been given a stop request? And so you hold your stop token, and then when the thread with the stop source are signals, requests of cancellation, requests that you stop, then the stop token is now signaled. And when you ask it, is there a stop signal? Then it will say yes. This is purely cooperative. If you don't check the flag in the stop token, then nothing happens. It's up to you to actually do the check. But it provides this mechanism where you don't need to know the circumstances under which the stop request has been made. The thread with the stop source makes the stop request, and then the thread with the token then can see that the stop has happened. And you can have multiple copies of the same token, so you can have multiple things stopped from the same request. So it's something you can pass around, and it allows it to tidy, but it is purely cooperative. So Dataflow, how it works is you create a stop source, you get a stop token from the stop source, and you pass that stop token to something that you're going to want to potentially cancel. New thread, new task, something like that. Then when you want the operation to stop, then you call request stop on our stop source. And then periodically in that thread or task, then you have to check how, call this stop requested function to check whether stopping has been requested. And then you actually need to stop if you're going to tidy up. You need to stop what you're doing, cancel, tidy up, and then carry on. And again, just to reiterate, if you don't check whether stop requested, then nothing happens. If you just check the flag and then do nothing, well, you've just ignored the signal and nothing happens. So it is entirely cooperative. It's on the onus on the code using it to check, but it does give you a means of doing this communication. It also integrates with standard condition variable any. And so this means that if you're waiting for something to happen, you've got a condition variable wait, then you can say, well, I'm waiting for this to happen, but you can cancel me. Here's my stop token. And so then if there is a stop signal that's been requested and the stop token is signaled, then your condition variable wait will stop, and you can then check the token, say, was I stopped, or did the thing I was waiting for actually happen? And so you can see, yes, I was stopped, so I will tidy up, finish my operation, and pack up and stop. And note this is condition variable any, because it's a little bit more flexible than standard condition variable. In order to support the variable types of mutex that it works with, then it has the additional implementation hooks that allow the stop token to integrate, whereas standard condition variable on its own usually is too low level integrated with the OS, and there isn't the means for hooking in a stop token. But from a user's perspective, you just change standard condition variable to standard condition variable any, and now you can use stop tokens. The API is the same. And so just to see how that looks in code, we need a mutex, and we've got some data that we're protecting. In this case, it's a queue. We're waiting queue of data, and we're going to wait for some data to come on our queue, and we pass in our stop token. We lock the mutex, and then we wait. We're going to wait until our queue is not empty, or until the stop token is signaled. So we need to pass that in as the last parameter. And in this case, then if when the wait returns, then it returns false, which means that the queue was still empty. Then we're just going to throw an exception to say our operation was cancelled. Tidy up. Obviously, you don't have to deal with an exception. You can just return, or you can do some different processing or whatever. But to make this simple, we're just going to throw an exception here. And if the wait returned true, then there was actually data, so we can retrieve the data from the queue and return it. So that's just how you might use that if you're waiting for a queue with condition variable anyway, but the addition of this stop token means that we can tell that we were interrupted. It's not just condition variables that can be interrupted, though. You might have something that is a blocking operation, like some file I/O, and that you want to interrupt. And then this is where the additional feature of StopCallback comes to play, because this allows you to provide a callback that is invoked when the stop request is made. And so if we're reading a file, if it's a big file, it could be a long operation, or even if it's a small file, it can be long in terms of CPU cycles, and you might still want to interrupt it. So we have our stop token, we have a file path, we open our file to get a file handle. Now we register our callback, and we pass in this little lambda that's going to cancel the I/O, passing the handle. And if the stop token has got a stop request, then that callback will be invoked, and then our I/O is cancelled. And so even though on the next line we're calling read data, which we're saying is a blocking I/O call that's potentially long and slow, because it's a blocking OS call. It's not going to actively check the stop token itself, but we've registered this callback, and this cancel IO function we're saying is the counterpart OS feature that allows us to interrupt that IO operation on that handle. So we say cancel. So if somebody requests to stop from another thread, then it will call cancel IO, and our read data will be interrupted. And obviously, how that then processes it, whether it throws an exception or whether it just returns partial data or whatever, that's up to what the actual function does, and you'll have to check. But it does allow us to provide this means of interrupting things if there is a library level facility that allows something to be interrupted, even if it's completely separate from stop tokens. And then when the stop callback is destructed, so at the end of this block, then cancel IO will never be called. So it's safe to our callback is destroyed before our handle is destroyed, and so it's safe. Cancel IO will not be called on an active handle. We don't have to worry about it being called when we've already returned from this function or anything like that. It's worth pointing out, just as a by the by, that stop callback is in fact a templated class, but because this is C++20, we don't need to specify the template arguments. We can use the template argument deduction guidelines introduced in C++17, and just to make that all go away. So you don't need to specify the type of the callback. It just works. It just deduces it, and you just say stop callback. Okay, so we also have a new thread class. Now, our new thread class is called a JThread. It was originally joining thread, but joining thread is a bit long-winded, and so JThread it is. And obviously, the reason it's called JThread, joining thread, is that it calls join when you destroy it in the destructor. Normally, standard thread, as I mentioned in the intro, in the destructor, if you haven't joined, then it terminates your program. With JThread, when you hit the destructor, then it joins with the thread and then waits for it to finish and help. This makes it easier to have some form of structured concurrency, so that you start your threads and then you process things, and then when the thread objects are destroyed, then you know that all the threads have been finished and you can process things.
Sorry, Anthony, we have a question.
Okay.
Yeah. So it's about stop source. So is there a way for stop source to check if thread was really cancelled and after request, or is it still running?
So no, there isn't a way to check whether actually anybody has done anything with the with your stop request. All you can do is check, have I requested stop? And yes, but yes, there's no way of checking what happened to that signal. You can't tell whether somebody has even seen the signal, and if they did see the signal, then you definitely can't tell what they've done with it, because it's perfectly legitimate code to say
to ignore
to ignore the stop request. So there isn't a mechanism for doing that. You could build one. You could use stop token to do that check backwards. You could have one source that signaled a request and another, and use the second one to say, have I actually been stopped coming the other way? Has that happened? But that's not its intended use. And like anything else, you need to design your own mechanism for that.
Thank you.
Okay. So JThread, it integrates with stop token as well. So one of the reasons why standard thread didn't join was because if something goes wrong, and say you've got an exception, and so the thread is being destroyed on an exceptional path, then the thread might still be waiting for something that's now not going to happen because of the exception, and because the code that was going to trigger the event or whatever didn't happen. And so then you would end up with deadlock. You would the destructor for the thread class would then wait for the thread to finish, but the thread is waiting for them for something else to happen that's just not going to. And so a key part of JThread is that it calls request stop on the stop token that has been passed to this background thread, so that you know that not only is the class waiting for it, but actually the background thread has been told to stop. Obviously, again, you still have to check, but it now is this mechanism that you can see that the thread has been asked to stop, and so you can use that to help interrupt whatever was that was happening. So let's see that in code. We have our thread function, and it takes a stop token as its first argument, and then additional arguments, whatever. And again, while we're not being asked to stop, we can just do some stuff. And then we're going to spawn that in our function foo. We're going to create a JThread T, pass in our thread function and the arguments. The string we were given, the number 42, they will map to arg1 and arg2 up in the thread function. And then we're going to do stuff in the meantime. And then finally, at the end of the block, the destructor will request stop and then wait for the thread to finish. And so this all processes nicely. It is backwards compatible with standard thread. So if your function doesn't take a stop token, then that's okay. It just doesn't, if you pass in just the arguments that it's expecting, and if it doesn't take a stop token, then it just isn't given one. And the stop request part then doesn't have any effect because there's nobody listening. But if you do take a stop token, then you're given one that's tied to the thread object. Okay. So don't just have new stop cancellation and JThread, we also have new synchronization facilities. We have 3. We have latches, we have barriers, and we have semaphores. Now, latches are if you've done electronics, it's like a hardware latch. It's a single-use counter that it counts down until it hits 0. When it hits 0, then it is signaled, and it is now signaled forever. Until that object is destroyed, it is signaled. You create it with the initial count, and then the threads decrease the count as they as the signal that something has happened. And then when all the threads of when the count has been decreased to 0, then it is permanently signaled. And this allows waiting threads to be woken. The threads that wait for it don't have to be directly associated to the threads doing the signaling. So you can create a latch. You can have 5 threads that are doing the processing that's going to count down the latch, and you can have a different set of threads that are waiting for that latch to be signaled, or they can be the same thread. You can signal the latch and then wait for it, and there's a special function for that. But it's when you're waiting for some bunch of things to happen. So,
can we again? Sorry.
Yes. Go ahead.
Another question. Again, we usually one topic behind. Because when you stop talking about this topic, people start to write question. They realize that it's all about this. So stop source token sounds like a named future promise one-time signal pair, right? That you can just shoot it one time. And what are alternatives for multi-shot signaling cross-thread channel considered?
So no, and there isn't. It is deliberately a one-shot signal for requesting that you stopped, generally on the basis that you don't want to cancel something twice, because if you cancelled it the first time, then either it's successfully cancelled or it's not cancelable anymore.
I think the question is more about, so it sounds like you just basically there's a one-time shot, right? But maybe there is an alternative for several. So not naming it, not naming it cancel or stop talking, but basically like stuff to signal multiple times, to send signal multiple times.
Yes. So obviously there are definitely use cases for that. We don't have a library facility for doing that. That's in some sense that's like a multi-threaded queue. You've got this data, and in this it might just be a simple true or false flag that is your data, but it is a series of data. Channels and queues are the sorts of things that that's called. We don't currently have any of those. There are proposed ones, which I'll talk about later in the talk. But there isn't anything at the moment for that sort of repeated signaling that is in the standard.
Okay, thank you.
Okay, so we're waiting for our task with our latch. In red, we can see we've created a latch. We've got a thread count. We've then got some data. It's an array of data, one for each thread. We've got our JThreads, and we created a JThread for each entry. It's very simple task here. We're going to create the data to go in the corresponding array entry and then count down. And then we're going to do some more stuff in the background just to show that we're not actually waiting for the threads to finish. We're waiting for the countdown signal. Then the main thread can wait. At this point where it waits, it knows that all the threads have counted down their latch. So the data array is completely populated, and then we can process it. And so then that is correctly synchronized so that you know that all the entries in data can be accessed safely, even though the other threads might still be doing their extra stuff. They're still doing whatever do more stuff actually does, but that's okay because they've populated data. They're not touching that anymore, so we can now carry on and do our processing. So one thing that I use Latch for, and I use all the time, use standard Latch if it's available, or write my own if it wasn't, is for writing multi-threaded tests, because it's the closest that you can get without having control of the scheduler to actually setting things up how you want in terms of all the threads running at the right point in code. You set up the test data, you create your latch, and you create the test threads. And then right before the body of code that you're trying to run concurrently, it might be different sections on each thread, or it might be the same thing. You've got 5 threads that are concurrently trying to access the same data structure or whatever. Then just before doing the test code, you call latch arrive and wait. And this counts down the latch by 1 and then waits for the latch to be signaled. And so if the latch has got the same count as the number of threads, then when all the threads are ready, then they can then all release together and they can all do their concurrent processing. So at this point, you've got over the hurdle of creating the threads and waiting for them to start. So many tests. You've got 5 threads in your test. You start at thread 1. Actually, thread 1, your main thread looks like it starts all the threads and then does some processing and then waits for them all to finish. But what can actually happen is the first thread starts, first thread does some processing, then the main thread starts the second thread, then that does some processing. Sometimes even one of your threads might have finished before the last one has actually started. And so you haven't got that concurrent access you're actually hoping. You're not testing the concurrent processing that you would like to. And so by putting the latch in there, then you've actually meant all my threads are ready to run. They're right before, obviously, still the scheduler might delay things, but they're right there, ready to go, ready to run the code that you're trying to test. So that's the closest that you can do unless you've got control of the scheduler. And so I find that a really useful pattern for multi-threaded tests. So this moves us on to barriers. Barriers are the counterpart to latch, except they're reusable. So when the count reaches 0, then it is reset back to the maximum, and then it counts down again. But as a consequence, it means that actually only the threads that are involved in the count can wait, because otherwise you're waiting for something that's going to happen multiple times. And so you lose the synchronization. And there's also this extra aspect of a completion function. So you construct your barrier set your count and the completion function, and then your threads arrive at the barrier and wait for the barrier to be signaled. And then when the count reaches 0, then it's signaled and the threads are released. The completion function is called on precisely one of the threads, and then the count is reset and the threads can continue processing. And so usually if you're doing a repeated set of processing, so then and you've spawn a set of threads to do each chunk, and then when everything's finished on that chunk, then you're going to wait for them all to finish, do some form of completion, and then start again. So if you're encoding a video, for example, then you might, on each frame, then you might decide that I can run multiple tasks that are going to encode different parts of the video frame. If I've got at a just simple level, if I've got 4 threads, then I might have one doing the top left, one doing the top right, one doing the bottom left, one doing the bottom right. 4 threads processing my video frame. When all 4 threads have finished their processing, then I might ship out the frame to be sent over the network for real-time streaming or whatever, sent to disk, and then I can start processing the next frame. And so you can use a barrier to do that sort of synchronization at the end. And your completion function can do the network ship out of the frame ready for and preparing the next one. So this is it's a loop synchronization is what you use barriers for. So yeah, the completion function allows you to do something between the loops, pass the result onto another step, write to a file, send to a network, whatever it is. When you've got these parallel tasks that you're trying to do in sync, but each multiple things can happen together, and then we send out then they need to move on to the next step only when everything's done on the current one. So just show you how to encode. We have a barrier. This time we have to specify what the type of completion function is. In this case, it's any old function that takes no parameters and returns void. It could be anything. The return type is ignored, so it doesn't really matter. But and it needs to take no parameters because there aren't any. But in principle, it can be anything callable. And you pass in the number of threads and actually then the task that's going to be called. So we have our thread. It's got a stop token, and so whilst it's doing stuff, whilst we haven't been stopped, we're going to do stuff. And this is our worker number, and then we're going to arrive and wait. So we're going to wait for all the other workers to be ready, and then we can loop round and we can again do the next set of stuff that's related for what the task is that we're doing for this particular worker thread. Okay. Semaphores are the third completely new library feature, and if you've done multi-threading processing in other languages or with other libraries, you might have encountered semaphores before. They're a very simple concept. The idea is we have a number of available slots, and if you acquire a slot on the semaphore, it decreases the count, and then you can release a slot and it increases the count. And if you try and acquire it when the count is already 0, then it will either block if you make a blocking call, or it will fail if you make a non-blocking call. And then the thing that makes it separate from a mutex is that you don't have to have the same thread that calls release that called acquire. There's not this direct relationship. And obviously, there's multiple. You can have a count of 20 or 200 or 3,000, 5 million. And you can call acquire that many times, and then when it hits 0, then things will start blocking. So it's a very flexible synchronization mechanism. You can use a semaphore to do anything. You can build a mutex with a semaphore. You can build a condition variable with a semaphore. You can build futures with semaphores, and other things besides. But getting it right is quite tricky. But it's flexible, and implementing a semaphore is hard and often ties directly into the OS for the signaling. And so it's now provided as part of the standard library. So a special case, we have a binary semaphore, and in binary, because it's got 2 states, it's either 1 slot free or no slots free. And that is a simple thing, can be used as a mutex. And so we actually have this standard binary semaphore, which is an alias for counting semaphore of 1, 1 being the maximum count. So it's got 2 states, 0 and 1. Otherwise, we've got counting semaphore as is the general semaphore type. And so we have acquire, which is blocking, and then also like in mutexes, we have try lock. On semaphore, we've got try acquire, and then a try acquire for and try acquire until, which take timeouts. Either for takes a duration. For I'm going to wait for 3 seconds and try and acquire, and if I don't, then I'll fail. Or try acquire until a certain point in time. Again, just like the mutex try locks. So we have try lock for and try lock until with timeouts. And they return false if you can't acquire. So just to see what it looks like, again, we have counting semaphore. We're going to say 5 is our maximum. And we're going to start with 5. You can start with a different number. You could, there's lots of uses of semaphores where you start at 0, and even though you've got some maximum. But in this case, you specify 5. So we have our function. It's going to acquire a slot. It's going to do something. It's then going to release a slot. And we know that there are at most 5 threads calling do stuff, because our semaphore has a maximum of 5. And so first 5 threads that call func will successfully acquire. They will then do stuff. Then they will release. And as they do, then the count goes back up again. And so other threads can now acquire. But there will be no more than 5 at any point inside do stuff. Those are the things that are completely new, but it's not the only changes. We've also been quite a lot of updates to the atomics facilities in C++20. In particular, we've had low-level waiting added, so you can wait for your atomic variable to change value. We've got atomic smart pointers, so we can have atomic of shared pointer, and atomic ref, which allows you to do atomic operations on an object that was not declared atomic in the first instance. So let's have a look. Okay, so for waiting, then every atomic of t now has a wait member function, which waits for it to change. You pass in the old value, and it will return when the value has changed, and somebody is called notify, or spuriously. And so it's very much like a low-level condition variable. It has the same sorts of downsides in terms of having to deal with spurious wake-ups. So you have to make sure that you check things. Wait it has a void return, and so it doesn't tell you what the value was. You just know that you've been woken, so you need to then recheck the value to make sure that it's been changed. But this can be used as a low-level synchronization thing, and it's particularly good if you're trying to write lock-free algorithms and you need to wait. And so if you wanted to use condition variable for waiting, then you'd then have to use a mutex lock. And, well, having to use a mutex lock in what would otherwise be a lock-free algorithm seems a bit of a contradiction there. So you can just use your atomic wait functions instead of low-level to do low-level waiting. Obviously, it's still a blocking wait, which if you're trying to write wait-free code, well, there's a wait there. It's not wait-free, but it does mean that then you can have it completely wait-free on the fast path, and then only when you're actually having to the program logic says that you have to wait, then is there any waiting happening. Okay. So we also have atomic shared pointer t and atomic weak pointer t. Now, this is important because normally the parameter to an atomic has to be something that is trivially copyable. And standard shared pointer is clearly not trivially copyable. Now, it's got to increase a reference count when you copy it, or decrease a reference count if you overwrite it or destroy it. And that doesn't work with a normal standard atomic. So these are specializations. And like all the normal standard atomics specializations, they may or may not be lock-free. It can use a mutex internally. And in fact, lots of implementations do, because writing a lock-free atomic shared pointer is A, really hard, and B, actually has potential implementation cost in terms of memory and time and execution complexity that it doesn't. It is not necessarily faster than just using a mutex. And so lots of implementations just take the idea that they'll just use mutex. But either way, if you have a shared pointer T and a mutex, then atomic shared pointer T is better because it directly reflects what you're using. There isn't the possibility of not locking the mutex and accessing it directly by accident. So it is a better upgrade if the only thing protected by that mutex was your shared pointer.
And again, we have a question.
Okay.
And again, unfortunately, a bit back. So the question about semaphore, why semaphore is a template, why its capacity can be specified at runtime?
Okay, so it is a template because it has to store the value, and so some implementations on some platforms can have a different implementation depending. Binary semaphore might be one implementation. A semaphore with a count less than 32 might be a different implementation. Because they might be able to have a bitmap of 32 bit fields for each of the values as they counted. Or whereas on the same platform, then a semaphore with a count of 5 million might have to use a different algorithm altogether because now it has to use a proper integer and count. And so having that template allows different implementations for different values. And then obviously the value is specified at runtime as the initial value so that you can use it on algorithms that vary depending what the initial value is.
Thank you. And another question, we actually have a couple. And I think this one goes even far back. So does finish task executes on the same thread where barrier was created?
Oh, so with the barrier, the completion function, it runs on one of the threads that is waiting for the barrier, but you don't know which one.
I think you mentioned that. I think people started to send questions because we stopped for the questions. So what's the cost of having ability to wait on the stud atomic? It's actually a lot of question.
Yeah.
Is
okay.
Size opens?
Okay, so probably best if we leave most of the questions at the end, but just if we pick a couple, go now. So the one that you just asked about the weight on atomics, there is no cost in terms of size or performance generally if you do not use weight. On the platforms that provide it, then they use OS-specific facilities like futexes and weight on address. They allocate structures in the kernel rather than actually in your program visible code. So atomic of int is still the same size as an int, probably, if it's lock-free. And that doesn't change just because it now supports weight. Yes.
Thank you. It's actually the last question. All the other was just thank comments. So
okay,
we're good to go.
So yeah, so atomic shared pointer. If you're going to use a mutex and a shared pointer, and that's all you're using with your mutex, use atomic shared pointer instead. It's better. Just to see how that might work. If we can have a stack which can shared pointers pointing to each node, and we can make that a thread safe stack by using atomic of shared pointer on our head node, and then we can push things on and everything is synchronized correctly. Note that if you're doing this, if you're using shared pointer in your stack, then your destructor needs to remove the nodes, because otherwise, then if you've got a lot of things on your stack, when you destroy it, then it recurses down into as destroying each shared pointer in the turn. So if you've got 5 million nodes on your stack, then you end up with 5 million destructor calls deep, and that's probably going to cause the stack overflow. So if you remove the nodes, here we've got our while loop. While there's a value, then we're going to call pop. Then that avoids that because it does it at a single level. So that's just a general principle about using shared pointer and stacks. But so from the push perspective, then we create a new node with make shared. We read what the existing head value is and into our next pointer, and then we use compare exchange, and we just check can we swap the next pointer for our new node, and if we can, then we're fine, and if we can't, then we have to move on. So it's a very simple step, and that just works, and that is thread safe. And similarly, on the other hand, when we're trying to remove a value, then if there's a value to remove, then we try and swap the head for the next value, and this just works, and it avoids lots of the pitfalls. If you've ever looked at trying to write lock-free stacks, then trying to do this sort of thing without having memory leaks or other memory reclamation problems is hard. But with shared pointers and atomic shared pointers, it just works. It's dead easy. Obviously, this is only lock-free if your atomic shared pointer implementation is lock-free. And like I said, it might not be, and lots of popular implementations, it is not lock-free, but it is still better to do this way than to use a shared pointer and a mutex, because the library knows how to do this better. It will have an internal mutex that is optimized for doing just this, rather than a general purpose one that you get from standard mutex. Okay, so the final part on standard atomic on the atomics is atomic ref, and this allows you to perform atomic operations on non-atomics as if they were atomic. So particularly if you've got a binary packed data structure, or you're sharing it with C, or it's coming over the network as you've got a particular binary structure, but you want to share it with multiple threads. So then you can say, well, there's this struct field, and I'm going to use an atomic ref for that. And so now I can then access that as if it was an atomic, and it's all correctly synchronized. But you must make sure that you only use atomic ref objects whilst you're accessing it, because otherwise then you do have a data race just the same, because you've then got this non-atomic an int, say, that you're accessing. And some of the accesses are protected because they've got an atomic ref, and others are not. And it's the ones that are not that cause your data race and a big problem. So now, just as an example, we might have our C struct, which has a count, and then we take an atomic ref of that count, and then we can just use that. And so we can call do stuff on multiple threads with the same struct, and that is all fine, provided that everybody uses the atomic ref. So that is one thing that when you need it, this is really helpful. But again, I wouldn't use it if you didn't need to. Okay, so coroutines is the last thing on my existing C++20 stuff. And fundamentally, a coroutine is a function, but it can be suspended mid-execution and then resumed later. So from a implementation perspective, it's like a callable object where the local variables suddenly become member variables of your object, and so you call it changes the data, and then returns, and then you call it again, and it changes the data and returns. And so, but resuming it returns from the suspension point, and obviously the values, local variables keep their values. So we've got stackless coroutines, which means it's just the single coroutine frame that's saved. Everything is localized. So we don't have to save the whole call stack. It's just that one function and its parameters and its local variables. And so you can, in principle, have millions of in-flight coroutines. And in theory, and it does happen in practice with some structures, then the overhead can be eliminated by the compiler completely. And Gore Nisharov, who implemented this, called disappearing coroutines. You start with something, coroutine that uses a generator or something to produce a sequence of values, and then you look at the generated code, and it's just the same as a for loop, because the compiler can see the coroutine and remove any unnecessary allocations and overhead. Whereas if it was having to save the whole call stack, it wouldn't necessarily be able to do that. So in principle, then you can use it with concurrency. If you have a coroutine friendly feature type, then we can have our async get data function that returns this. Then we can use the co-await keyword to wait for it in our coroutine, and that will then wait for the data and potentially run other tasks in the meantime, notify your scheduler that this task is suspended and waiting, and then again we can process and use co-return to return a value through the coroutine aware feature type. Now I say if you have a coroutine aware feature type, there are no coroutine library types available with C++20. So for that you need third-party libraries. But in principle, it's a great concurrency feature. And where you do have third-party libraries, this does make your code look better. So you can get CPP Coro from my colleague Lewis Baker. I think that's not been fully maintained for a while, but it's still there and is usable where it does work. And David Haim has also got his concurrent CPP library, which also works with coroutines and allows you to use concurrency stuff like thread pools with coroutines. So those are places you can go, or you can write your own, but bear in mind that is hard. So, okay, which moves us on to the final part of the talk, new concurrency features. So obviously the sense of things that might be coming up in the future is, well, anything anyone can think of. But things that are actively under discussion are things like we have a synchronization wrapper for tying a mutex and an object. We have executors, which is thread pools, and more than that, but at a very basic level, it's thread pools, and just generally how a structured means of concurrency. Then we've got coroutine library support. I mentioned it's not in C++20, but there are active discussions about how to make that happen. Other concurrent data structures like queues, and then general safe memory reclamation facilities to help if you're writing the concurrent data structures. So there's lots of things under discussion. These are just a sample. So start with a synchronization wrapper for ordinary objects. This is a proposal that I made because I think it's generally useful. Synchronized value is something I've written in production code many times. It encapsulates a mutex and a value. The idea is that you can't forget to lock a mutex. Like if you had a standard atomic of an int, it's always safe to use. Synchronized value provides that for general types. You can have synchronized value of standard string, synchronized value of standard vector of something, synchronized value of whatever. And so it's easy to lock across the whole operation, and then it also provides facilities for locking multiple together in order to perform operations across several. So if you want to return the value, it uses the interface is fundamentally this apply function, which is modeled after tuple apply. You pass in a function that you wish to run, which takes the reference of the type of the object that's protected, and also pass in the synchronized value. And so to get a value out, you pass in a lambda that returns the value. To append a new string, then you pass in a lambda that updates the value, or whatever. You can do anything, but the only thing is that you should not store that reference anywhere, because otherwise you're just exposing a back way of accessing the data, and that is not good. You don't want to do that, because the whole point of using this is to enforce the synchronization. Okay, and obviously then you can, like with tuples, you can apply across multiple values. So you just extend that. This is a bit like visit with variants. You pass in the function and multiple variants. In this case, you pass in the function and then multiple synchronized values, and it dereferences each of them, turns you the reference. You can then operate on those. You could modify them both, whatever, within that function, and know that it's safe. Okay, big thing is executors. Now, at the base level, an executor is an object that controls how and where and when a task is executed. And this is a broad concept, and thread pools are very specific specific case, you might have a GPU executor that runs things on a GPU, or if you've got hardware with different types of cores on, like the cell processor in a PS4, then you might have an executor that runs on one of the specific cores and things like that. But as a concept, then it's actually quite contains too many responsibilities. So the latest proposals, the standard execution proposal, splits things into 3 parts. We have a scheduler that is in charge of where a task is run and when, to an extent, depending. And in principle, yes, so it could be control also when, in terms of your scheduler could have timing functions. You then have a sender, which controls what the task actually is. It's going to send values to a receiver, which then says what to do with the result. And so as a general principle, then this is asynchronous pipelines, and the senders are chained to receivers, which chain then might have a new sender, which initiates, it goes to a new receiver, and so on and so on and so on, and a big pipeline to a final receiver that actually then stores or something, the final result. Alternatively, I mean, the processing in the meantime might have actually output down the network or whatever, so that final result might just be a success flag. But the scheduler then runs this pipeline, and the pipeline can, of course, have forks in it, so and loops and whatever. But it's a structured way of specifying concurrency. So our scheduler might be a thread pool, it might be a GPU scheduler, and then our receiver is usually, you don't write a receiver, you use the provided ones like execution then or sync wait, because you focus on constructing the senders with tasks. So you can just use execute, which sends a task onto your scheduler, but this detaches the work, so you can't wait for it. So you might want to split it up into steps. You might want to do schedule and then call then to here's the task, and then start detached, actually do start. Or you could, of course, call sync wait rather than ensure started to make sure that it starts, and then call sync wait to get the result if you wanted to wait for it. You can chain things. We have then, and then we call then again. So we found the answer. So we get 42. It's going to be passed on. We're going to find the question. And then I say pipelines. Well, if you're familiar with Unix pipes, you can use the pipe character. Execution schedule pipe. Execution then pipe. Execution then. Pass it all through, and then we can call sync wait in the end. So it provides us this pipeline structured execution. This is, I think, this is the way that it's going to go. This is the way the Concurrency Committee, SG1, part of the C++ Standards Committee, really likes this direction. So we're looking to make sure that this is the way we go. Hopefully, we're going to iron out the wrinkles, but for C++ 23, but that's not guaranteed because the cutoff is January. And so we've really tight time frame to get this finished. But we've got a proposal, we've got an implementation. Hopefully we can make it all, iron out the wrinkles, make it all work. Okay, yeah, so you might obviously have errors. You can handle errors as part of your pipeline with this upon error receiver. Or alternatively, you can catch exceptions that get thrown out of sync wait at the end. If you actually want to try this out yourself, then Facebook have provided libunifx, which is their implementation of this, and they use it in production. It's good. It's hard. It's robust. You can try it out yourself. See how it works. Okay. Coroutines. I said we want coroutine support. Well, the senders, I hope that we will get to see something like task of T as coroutine support. And so then you can co-await a task and co-return, and actually deal with that in scheduling. We don't have concrete proposals for that as a whole, but we do have partial support in the senders and receivers execution proposal. So all the waitables are automatically senders. So you can wait for your coroutine task with sync wait. You can pipe it through then, and the library will sort it all out. You can also, some senders are awaitable. So depending on quite how it's been written, then you might find that you can co-await a sender that you've got from execution schedule and execution then. So there's lots of the hooks are there for making it complete, but it's not currently part of the proposal. So we're really just starting the hook, starting that framework. So probably there's not going to be proper coroutine support in C++ 23, but it's really going to be much easier for libraries to provide that facility without having to rewrite the complete coroutine framework themselves, because we've got this senders and receivers structure that can be used with the hooks there for making it work with coroutines. So I mentioned concurrent data structures. We often need them. We need queues. We need hash maps. We have standardization proposals for these. Queues are used everywhere. For message queues, typically, if you're writing using the actor model, then you want message queues between all your actors. The question earlier was about, do we have means of having repeated signals? Well, a queue is what you would essentially be using. So we have proposal for queues. Likewise, hash maps are generally used across all sorts of platforms for providing synchronized data structure access. And so again, we have a proposal for that. So simple thing, if you're using a queue, you're going to push data on, you're going to pop data off. We want this to be able to work across threads, but potentially also with multiple consumers or multiple producers. So there's different ways that can be implemented depending, but at the very basics, that's what we need to happen. And again, this is covered by the proposals. If you've got a hash map and if you've just got a basic hash map and you use a mutex, then that's really going to sap performance if that is got highly contended concurrent access. And you can design your hash map better to work with multiple threads on concurrent access, even if it uses mutexes internally. Just as a very basic example, it might have a separate mutex for each hash bucket, for example. And that increases the potential for concurrency by the number of hash buckets. Obviously, there are more complicated algorithms. You can have lock-free concurrent hash maps, or ones that are lock-free on the read side, but have mutex-like synchronization for modifications. So there's lots of scope there. These are covered by the proposals that we've got for concurrent hash maps. But if you're writing these yourself, then you need a safe memory reclamation facility. And we have these in the Concurrency TS version 2, the second Concurrency TS, which is the new library facilities which are actively being considered. So I mentioned earlier synchronized value. Synchronized value is also targeted at the Concurrency TS, but RCU and hazard pointers have been already accepted. We have implementations for those. RCU, short for read, copy, update, is used heavily in the Linux kernel. It provides us with lock-free read operations, but then you have to do synchronization when you wish to do any modifications to your data structure. So if you're trying to delete an entry, then you have to say, well, this is the entry I wish to delete. I'm going to set it aside and update the data structure with it out and then reclaim it later. And you can do a actual blocking call right there to wait until it's safe to reclaim, or you can literally defer it to a background thread. And hazard pointers, again, it's about deferred deletion. So we have a different set of performance trade-offs saying, well, I'm trying to access this, so I'm going to store a hazard pointer that points to this thing that I'm trying to access. Don't you dare delete it whilst I'm touching it. And then if it's removed from the data structure or modified, then you can then again, clean that up in the background in some way. So it's a different mechanism for essentially the same thing, deferred reclamation, but doing it safely when you've got concurrent accesses. So there are concrete proposal papers for these, if you want to look at them. These are their paper numbers. If you've got the PDF for this presentation, those are links you can click on. And then you can actually read what the details are and see what is currently up for discussion. Like I said, these are only proposals. They may change, but if you've got any concrete comments, then the authors, I'm sure, will be glad to hear your point of view and integrate your comments into future versions of the proposals. As Sergey mentioned at the beginning, I have a book, C++ Concurrency in Action. The second edition only covers C++ 17 and the first Concurrency TS, but latches and barriers are in the Concurrency TS, so the API is pretty much very similar to what was in the TS, so that is covered in the book. There is going to be an addendum for C++ 20, which will be a downloadable PDF for anyone who's bought the first edition. Okay, that is the end of my talk. So I'm going to say goodbye to everybody who's watching, but I believe that we have question and answer session following on.
So we will wait everyone in the discussion in the Zoom. The link is posted. Thank you, Anthony, for the great talk.